There's so much to tell about John. I know John for a while. He started over in the East Coast. Dalhousie is a bachelor in engineering physics. Then he went to UBC, where he was blessed to meet Stephen Morris. Because after maybe a year or two, because they couldn't be in the same place, he decided to go for a PhD in Simon Fraser. John is a professor in Guelph since 1990 for almost 30 years. Time flies. His interests are very, very broad. If you look at his webpage, things that happen in polymers, biopolymers, bacterial thin films, bacterial films, patterns, really what would be a soft condense metaphysicist. And in the last maybe decade, he kind of became softer and softer until he crossed the path to biological physics. So if you look, he was a tier 1 CRC chair in soft condense matter, but now he's soft condense matter and biological physics. So he's the director of nanoscience program at Guelph. The topic for today, he's going to tell us about some weird stuff that we can find in the core. Nanoparticles that can hold a ridiculous amount of water, amongst other weird properties. And John and I will meet often at conference CAP, at biophysics meetings, and I can't remember. I do remember actually. In Montreal in May, we almost studied nanoparticles in single molecules at 2 o'clock in the night. So you can see he has interests that are diverse, and he was director of food and nanoscience program. I think he learned something from looking at food and drinks, and he'll tell us something exciting about corn. What do you think? So let's welcome John.
Thanks very much, Claudio. And thank you for the invitation to come here and tell you about something. This is actually a fun story, so be prepared. This is about serendipity, right, which we all know is one of the best things about science, the way science sometimes moves forward. And so this started off as a side project in my group and now consumes most of what we do. So what I want to do is start by telling you about some particles that we discovered. I want to describe to you their unique structure. They are nature's dendrimer, or tree-like molecule. And this leads to some interesting effects, such as nano-confined water. The particles themselves are soft and deformable, and this leads to some interesting soft colloid and glassy physics. And if I have time at the end, I'll tell you a little bit about the applications of these particles, something which we have spun off into a spin-off company called Mirexus. So as I mentioned, it started with serendipity. I was involved in a fundamental, and I like to mention that specifically, a fundamental research collaboration with a very good microbiologist, Terry Beveridge, also at Guelph. And we were trying to figure out how bacteria stick to surfaces. Okay, so if you want to figure out how something sticks to a surface, you might want to look at the surface. So part of what we did was to run a complicated chemical procedure to isolate some of the molecules at the surface of the bacteria, something called lipopolysaccharides, or LPS. And in the course of doing this multi-step chemical process, it generated a waste product. Okay? And it looked kind of cool. Okay? It had the property of opalescence, so different colors from different directions. So here I show a globe of this material that is lit from the left, so it looks blue in reflection, and then this spherical container kind of acts like a lens, and it focuses the transmitted light, so you can see that it's orangish-red in transmission. So because it looked cool, the postdoc didn't throw it out. He kept it. And it's actually sat on the shelf for a long time before we got around to actually measuring it using one of our fancy atomic force microscopes. And it was one of those sort of eureka moments, because instead of looking like garbage, which is what we expected, we found that it looked instead like this. So all of these tiny little particles, about 35 nanometers in diameter, that were all very much the same size. Okay? And so what we had was really these particles suspended in water. So this is literally just that suspension that has been dried down onto a mica surface. So these turn out to be rather remarkable particles. We didn't know what we had to begin with, so of course we used all of the techniques at our disposal. Being at a university, it's a great place for having access to different techniques, from various microscopies to various spectroscopies and so on. And eventually we figured out that this was actually a form of glycogen. Okay, so most people know about glycogen. We have glycogen in our bodies. Glycogen is a rather interesting molecule. It's chemically very simple, made up only of glucose monomers, but they're connected together in a very unique way that allows them to form into these very dense, compact, small nanoparticles. So you can think of these as little balls, sugar balls. And they have interesting properties in their own, but you can also think about doing rather simple sugar chemistry or carbohydrate chemistry to modify the outside surface, and that can change its properties and make them tunable. The really neat thing about these particles is that we discovered, okay, so first of all, I should say, we discovered them in bacteria, okay, and isolated micrograms of the stuff, and then thought about scaling up the production to see if we could make more. Turns out bacteria are not very helpful in that respect. It's kind of difficult to scale up production of something like this using bacteria, using fermentation techniques and other techniques that are abhorrent to most physicists. So our team actually discovered that similar particles were actually produced by certain plants, and in particular sweet corn. Okay, and so we were able to switch from generating these particles in bacteria to, I shouldn't say generating, I should say isolating and purifying these particles. The organism does all of the hard work in making these molecules. All we have to do is extract and purify these particles without disrupting their structure. And so what we have now is the ability to produce very large quantities of these particles from sweet corn. We're sort of a darling of the Ontario Ministry of Agriculture and Food because, hey, you can get something that's really valuable out of something as common as a corn crop. And not only are the particles biodegradable and even edible, as we all know, you've all eaten this stuff, no harsh chemicals or enzymes are necessary to isolate and purify them. It's all physical separation techniques. Okay? So it's not only are the particles green, but the process to isolate and purify them is also green. Okay, so as I mentioned, chemically nothing special, a bunch of glucose bonded together, but bonded together in a very special way. So this is what I would call nature's dendrimer. So a dendrimer is a molecule which is typically rendered like this, okay? So you start with a seed, and from that seed, you have linear chains that grow and then branch and grow and branch and grow and branch. So the typical way of drawing this is like this, and that leads you to believe that you have a highly branched outer surface and maybe you have a hollow core. Well, that's not the case, because what happens is that these sugar chains are actually quite flexible, and they will actually fold back in to fill in all of the available space. So what you end up with is basically a uniform density core, highly branched throughout. And here's a rendition of this that has been generated by one of our collaborators, Hendrik de Haan at UOIT, in which he's basically grown these particles given the constraints that we've given him from our experiments. And this is kind of like what they look like. So these particles have really quite interesting and somewhat unique properties. One thing that we noted at the outset was that they're all pretty much the same size. They have monodispersity. And this is actually a little bit difficult to understand. The common explanation as to why that might be would be that it grows and branches and grows and branches until it gets so highly branched that the enzymes that are necessary for further growth can't access the sites. I'm not sure if that's strictly true. I think there's something more to it, and this is something we're looking into. What is really remarkable is its interaction with water. Okay, so these particles have extraordinary water retention. If you put them into water, they have a very low viscosity, and they're highly stable. Suspensions of these particles in water are stable for years, even though the charge on the particles is almost zero. So they're not, their stability is not described by the ordinary DLVO theory. There's something more to it. So water is special, and so we have done a lot of different studies to study how water interacts with these particles. We've done neutron scattering down at Oak Ridge National Lab with John Katsaris' group. And in these measurements, we did both small angle neutron scattering and quasi-elastic neutron scattering. And these measurements told us an awful lot that I'm not going to tell you about today. They told us the size of the particles. They told us about the radial density profile. They allowed us to determine the molecular weight, or the molar mass, of both the hydrated particles and the dry particles. And they also, the quasi-elastic measurements allowed us to observe dynamics of water inside the particles and show that it was about a factor of 5 or 6 slower than it is in bulk water. What I'm going to focus on instead are these last 3 techniques that tell us more about water. Infrared spectroscopy, typically maybe the domain of chemists, but you can do some good physics with it. In this technique, we're looking at the absorption of infrared radiation by the OH bonds, of which there are many within the water and within the polysaccharide. And this tells us that we have highly structured, tightly bound water inside the particles. We can also make ultra-thin films of these particles and look at how they swell when we vary the relative humidity. And from that, we learn about short-range hydration forces. And I'll probably spend most of my time telling you about some rheology measurements of aqueous dispersions of these particles and how this tells us something about the interaction between the particles and how they can become highly deformed at very high loadings of the particles, leading to something called a colloidal glass. Okay, so let me say a few words about infrared spectroscopy. So basically, one can look at molecular vibrations with this technique and learn about things like the stretching of the OH bond. So if one does this for bulk water, you end up getting an absorbance peak that looks like this. And it's kind of complicated. Right? It's not a simple single peak. People analyze this peak as being made up of 3 different contributions. So we have highly ordered tetrahedral water, where almost all of the bonds are satisfied at the lowest wave number. And then we have a slightly less ordered component at a slightly larger wave number. And down here, it's basically highly disordered water. So what we did was to make films of our particles and compare them to 2 other polysaccharides with a very different chemical makeup. So I'm comparing here that OH stretching band for the phytoglycogen particles here, and then 2 other linear polysaccharides. One is called hyaluronic acid, which is the industry standard in moisturizing agents and cosmetic formulations. You even hear about it in TV commercials. And another chemically different polysaccharide that is called chitosan. And if you look at these spectra, you see that each of these plots consists of a series of spectra corresponding to different values of the relative humidity. So basically, the lowest spectrum here has the lowest relative humidity of about 5%, and then higher humidities as we move from the bottom to the top. So I look at these spectra and I go, okay, well, they're all very different. There's not much similarity. But what Mike thought of doing was to actually isolate the water contribution. So these spectra consist of OH stretches within the polysaccharide, within the water, as well as other stretching vibrations involving things like nitrogen. And so it's a big mess. But if you take each of these spectra and from that subtract the lowest relative humidity spectrum, you see something quite beautiful. You see a very strong similarity between the two linear polysaccharides. These look almost identical now, even though chemically they're very different. By doing that subtraction, we've subtracted away the polysaccharide, and we're just seeing the water signal. And then over here, we have the result for the phytoglycogen nanoparticles. And this series of spectra looks very different from these. And if you remember back 2 slides, I said that the highest degree of order, the tetrahedrally bonded water, corresponded to the lowest wave number. So if I look at these spectra, I see that I've got a big signal at the lowest wave number for the phytoglycogen, much larger than it is for these others. So this is telling us that these nanoparticles have inside them water which is highly connected and strongly bound. Okay? And this actually goes a long way towards explaining why it works so well as a moisturizing agent in cosmetics. You can sort of think of it as a slow release vehicle for water. So even though the humidity might be going up and down between daytime and nighttime, this will provide sort of a constant release of water that makes your skin actually feel better. We can think about this from the point of view of nano-confinement of water. And what is the effect of nano-confinement on the structure of water? Previous studies have been done on other biophysical molecules, and these have basically shown that the structure of the water is sensitive to confinement, but insensitive to the chemical environment. It really doesn't matter if you're looking at liposomes or polymers or micelles. You see the same kind of effects. And in general, the idea of confining the space available to water leads to a reduction in the number of hydrogen bonds, defects within that highly bonded structure, and reduces the water connectivity. However, in some cases, people have observed that nano-confinement leads to an increase in the degree of structure of water, in particular within cylindrical glass nanopores, similar to what we see in the phytoglycogen. So perhaps the water in the phytoglycogen is more highly ordered because we're forming well-ordered nanochannels along the helical chains that exist within this molecule, plus the fact that there are a whole bunch of hydroxyl groups that can participate in hydrogen bonding in the first place. Okay. Another measurement that we can do is to make ultra-thin films of these particles, and we can measure the swelling as we change the relative humidity. So what I show here is a plot of the film thickness as a function of relative humidity for 5 different films with 5 different starting film thicknesses, ranging from about 45 nanometers to about 90 nanometers. If I instead plot that as the film thickness divided by the lowest relative humidity value, H0, as a function of relative humidity, all of this data sort of collapses onto a single plot. Okay, so it's sort of a universal behavior. It doesn't matter what the initial film thickness is. The mechanism responsible for swelling is the same for all of these films within this range of film thicknesses. And one thing that we can do is we can interpret these results in terms of what's called a disjoining pressure, which acts across the thickness of the film. Okay, so this is a concept that was introduced by a famous physicist called Derjagen. And basically, you can think of the absorption of water as leading to a swelling, which is effectively a pressure which tends to increase the thickness or disjoin the film. Okay? So we can recast that swelling data as a plot of this disjoining pressure, which you can calculate, as a function of the distance between the different glucose units within the sample, assuming a simple model of a lattice model of the organization of these units. And what you find is that from this data, you can identify a decay length in the limit of low disjoining pressures. And this decay length actually depends upon the chain architecture. So we can compare, once again, our particles, which are based on glucose, to two other glucose-containing polymers, something called dextran, which is just mildly branched, and something called cellulose, which, as we know, is highly ordered and semi-crystalline. And this decay length of the hydration forces has a systematic variation on this parameter, with phytoglycogen falling between the loosely branched dextran result and the highly oriented and crystalline cellulose result. Okay, so the last thing I'm going to tell you about today, which is the thing I'll spend the most time on, is rheology measurements of what happens when you put these particles into water. So this is a plot of the viscosity of the dispersion relative to that of the water into which it's added as a function of the concentration of these particles. So as you can see on this plot, which is maybe not a good way to plot it, nothing happens until you get to very high concentrations. And in fact, the data looks much better if instead of plotting this on a linear vertical scale, I use a log scale. And then I see this beautiful dependence of the viscosity on the concentration. So this data is telling us several things. It's telling us that at reasonable concentrations, up until maybe 20%, there's only a modest increase in the viscosity of the dispersion. And that's unusual for polysaccharides. We know from the kitchen that if we have a sauce that we're making and we want to make it thicker, we add a little bit of cornstarch, right? And you don't have to add very much to make it a lot thicker. And to represent that, I've indicated a data point here corresponding to a common polysaccharide. It's not cornstarch, it's guar gum, but it's sort of the same thing. And just by putting in, you know, a % or two of this, you increase the viscosity by 4 orders of magnitude. So what's happening with our particles is inherently very different from what's happening with other common polysaccharides. And eventually, if I keep increasing the concentration, eventually it starts to take off and the viscosity diverges. And this is because you've added so many particles that you've forced them into contact, effectively making a gel-like or a solid-like structure at very high concentrations. So based on the shape of this kind of data, we can sort of think about these particles in the water as, you know, hitting each other, but always sort of bouncing off each other, never sticking, and acting essentially like billiard balls or hard spheres, with the proviso that we know that they're not actually that hard. But in terms of their interaction with other particles, we can think of them in terms of a hard sphere. Okay, so let me tell you how those measurements were done. Turns out that one has to be very careful in making up these dispersions so that they're properly mixed, especially at the highest concentrations. So we can sort of differentiate between two regimes in the data, concentrations less than 20% and concentrations greater than 20%. And if I go back, I see that that value of 20% is right about here, okay? Below this value of concentration, the dispersion of particles behaves as a Newtonian fluid. Okay? Above that concentration, it has nonlinear behavior. It behaves as a non-Newtonian fluid. 20% is sort of the distinguishing concentration. So below 20%, the viscosity is very low. We measure it using a so-called concentric cylinder geometry. And if we plot the stress versus the strain rate, we get a straight line. And the slope of that straight line is the viscosity, right? That's the definition of viscosity for a Newtonian fluid. And as you can see, it's a pretty good straight line. Above 20%, we observe the phenomenon of shear thinning. So if we increase the shear rate, what we see is that at low shear rates, we have some value, and if we continue to increase it, this drops off in a power law fashion, a phenomenon that's known as shear thinning. And essentially, you can think of the sample as consisting of layers of these spheres that are sliding over one another more easily than you might expect for a Newtonian fluid. And then using one of many nonlinear models, viscoelastic models, this one's called the Williamson Model, you can actually fit this data to get a good fit to all the data points, and in particular, you can identify what's called the zero shear value. And this is a value that I'll talk about. So I can compare the zero shear values that I get at low concentrations with those that I obtain from fits for the high concentrations. And when I do that, these measurements, I see data that looks like this. So over here on the left-hand side, these are all concentrations less than 20%, and these are all really quite linear if I plot the shear stress versus the shear strain rate. Over here on the right-hand side, I have a plot of viscosity versus strain rate showing the shear thinning behavior from 20% down here all the way up to 32% up here. The 32% sample is essentially a solid. You have to work really hard to get this properly mixed, and this is something that Hermes invested a lot of time and effort in doing. So what you can do is measure this zero shear viscosity value as a function of concentration. Remember, at low concentrations, we were using the concentric cylinders that are shown as blue points here. And at high concentrations, we were using a different geometry, the so-called cone and plate geometry. And as you can see, the values of this zero shear viscosity overlap very well, because we've taken measurements using both geometries for this crossover concentration value of 20%. So I can actually just treat this as a single data set. So how do I interpret this data? Well, I can look into the literature and see the theories that have been proposed to understand the mechanical properties of dispersions of particles. And the simplest theory that exists for such dispersions is something called the hard sphere theory. So this gets back to the idea of having billiard ball particles, hard particles that bounce off one another. The properties of such a dispersion are defined by a single parameter, the so-called volume fraction, the volume of the particles relative to the volume of the dispersion. And at low concentrations, or low volume fractions, the viscosity is described by the Einstein relationship, which says that the relative viscosity is 1 plus a correction term that's proportional to this volume fraction phi. Okay? At higher concentrations, the particles start to interact, and it's not so simple. And people have developed semi-empirical approaches to describe what happens as you approach very high volume fractions. And Krieger and Doherty came up with the semi-empirical relationship that's indicated here, a plot of the viscosity of the dispersion relative to that of the solvent as a function of volume fraction. And as you can see, it takes off, just like we saw in our data set. And this describes the divergence of the viscosity due to the packing of hard spheres at high volume fractions. At what volume fraction does the viscosity diverge? Well, you might expect that it would be the Keplerian value of 0.74, right? That would correspond to a lattice in which you have perfectly hexagonally packed spheres, right? You can never reach that in practice. What people have found is that the viscosity diverges. Dave Waits, for example, has found that the viscosity diverges instead at a lower value of the packing fraction, not 0.74, but 0.58, where the sample goes through what is referred to as a colloidal glass transition. Now, to relate our results to these simple theories, we need to do one more step. I showed you plots of the relative viscosity versus concentration. I have to convert the concentration values into volume fraction values so I can make this comparison. Well, typically that's an easy thing to do, except we have to keep in mind that these particles actually take up a lot of water. And so if I add dried particles, a powder, into water, a lot of the solvent is actually taken up by the particles. And so it's not a simple conversion between concentration and volume fraction. However, it's possible to work out what it is. It turns out that this conversion depends on quantities that we can measure. Things like the mass of the particles we add, the volume of water that we add, and then two quantities that we can measure independently: the amount of residual water that was in the dried particles, as well as the density of the hydrated particles. We measure this using a standard chemical procedure called a Karl-Fischer titration, and the density of the hydrated particles comes from the neutron scattering measurements. So with all of that information, we can make this conversion, and we can now plot our results of relative viscosity versus volume fraction. Okay, so you can see it has a different horizontal axis. So how does this compare with hard spheres? Well, it's quite different. This is a curve that corresponds to hard spheres that shows a divergence in the viscosity at a volume fraction of 0.58. Okay? And as you can see, there are big discrepancies between what you would expect from hard spheres and what we measure for our nanoparticles at the high values of the volume fraction. And this is consistent with the deformation of these particles at high volume fractions, which is also consistent with other measurements we've done. So let me just show you what I mean by that. Hard particles won't deform, but soft particles will. So if you think about increasing the volume fraction along this line, at low volume fractions, there's a lot of space between the particles. At some critical value, they start to touch. And if I continue to add particles, I will develop facets on these particles, and they'll basically fill in all of the available space. Okay? Where all of the available space is filled in at a volume fraction of 1. So what we've done is to look at the effect on the particles of packing them in really strongly. So Hermes was able to, by hand, but using a hand mixer, to prepare concentrations up to 32%, slightly over a volume fraction of 1. But by using osmotic pressure techniques, something called dialysis, we can reach much higher values. So here I show the results of putting a little bit of this dispersion into a little dialysis cassette, and then placing that dialysis cassette into a container that contains a solution of osmotically stressing molecules, osmolytes, things like polyethylene glycol or dextran. So Peter Rand at Brock University, who some of you know, was an expert in this field, and people still look at his old website to get calibration data for these types of measurements. So what Mike did was to place these dispersions into various concentrations of the osmotically stressing molecules. And these cassettes have a membrane, okay, which allows water to pass, but does not allow the phytoglycogen nanoparticles to pass, or the osmotically stressing molecules to pass. So on the outside, you have a certain osmotic pressure set by the polymer content that you've chosen. And so what will happen with the dispersion is either water will enter or water will leave that dispersion, such that the osmotic pressure inside and outside the dialysis cassette is equal. And in this way, one can achieve very high concentrations, so upwards of 60%. Okay, so here I show the result of leaving one of these samples for 10 days at a concentration of 25%. And this is what it looks like at about 50%. So it's really very solid at this point. What's interesting from this is that you can identify from this osmotic pressure versus concentration curve the situation that corresponds to packing the particles densely into the picture that I showed to you before. When the volume fraction is equal to 1, the concentration is about 30%. That corresponds to this data point, which means that I can read off the compressional modulus of the particle. So if I continue to add particles after I've filled in all of the available space, they will compress, right? So the osmotic pressure at the point where you've just filled all space gives you an estimate of the bulk modulus of the particles, which is about 20 kilopascals, which is pretty soft. In fact, this system of phytoglycogen and water, a very simple system, can be compared to more complicated soft colloid systems that have been developed synthetically over the years. This is a schematic picture of a series of different soft colloidal systems, ranging from really squishy ones like polymer coils up to hard spheres, passing through things like star polymers, microgels, emulsions, block copolymer micelles. And within this zoo of different structures, we can now add the system of phytoglycogen and water, which is comparable to the results that have been obtained for star polymers and microgels. So it's a new model soft colloid system. The native particles give you this result. But remember, we can also modify these particles. We can add stuff onto the outside. We can actually enzymatically or chemically degrade the particles and create a wide variety of different systems with different soft colloid properties. So let me tell you a little bit about the applications, because the applications are actually quite promising. After we found these particles and figured out what they were, we started to look at applications of these particles, figured out that we could obtain these particles from non-GMO corn. We actually got money from the Ontario government to grow corn in Elora, trying to figure out which varieties gave the best yield versus something called dry down behavior in the field. You have to learn about these things. And we were able to identify varieties that gave us a yield that was amazing. So if you think about the corn kernel and you think about the dry weight of the corn kernel, the yield of these particles in some varieties can be 40%. It's huge. We also got some money to do some pilot scale production, producing tens of kilograms of this stuff. At the same time, we realized that these particles were useful for a lot of different applications. And so we formed a spin-off company. And that company has been doing quite well. We have IP that's now protected by a patent portfolio, including composition of matter claims. We've received quite a bit of investment, about $20 million so far. And this has allowed us to grow the business and to hire lots of really smart young people, 18 full-time employees, 9 of them PhDs, very research-intensive company based in Guelph. And we've broken ground to build a new facility, a 12,000 square foot facility, which is currently being constructed on Downey Road in Guelph. that will allow us to produce 16 tons of this stuff per year. Okay? These particles have obtained approvals for use in cosmetics and food. People at Mirexus have worked together with customers to develop new products. How do we get our stuff into their stuff? Orders have been received and shipped, and products are now available. And if you're interested, I can show you something later. What's really remarkable about these particles is not only some of the properties that I was telling you about, but some of these other very appealing properties for use of a material for applications in the human body. So things like personal care or nutrition or biomedical applications. The particles are water-soluble, they're monodisperse, they're non-ionic, they're biocompatible, they're non-toxic, they're non-allergenic, they're biodegradable, they come from a renewable resource. It almost sounds too good to be true, actually. And so because of this, it's gained a lot of traction within the marketplace. The efforts at Mirexus have sort of been divided into these three different areas. Personal care. So this would involve adding the particles into a formulation because of its unique moisturizing capability. However, earlier this year, they ran a third-party clinical trial in the deep south of the US where people have a lot of skin damage from the sun, and they found evidence for anti-aging properties. So that means it basically rejuvenates the skin, removes wrinkles. Wow. And it's actually based on science. Okay. Another application area, which is intriguing, is the idea of stabilizing and solubilizing bioactive compounds, many of which are notoriously difficult to solubilize in nutrition products. Vitamin water contains vitamins, but those vitamins aren't accessible to your body, so it's kind of useless. So we have that kind of application area, but the most promising area by far is the biomedical side. And so by taking these particles, on their own, they really don't have much biomedical application except in rejuvenating skin cells. But if you modify the outside surface, you can create novel forms of antimicrobials, anti-infectives. You can think about this as a drug delivery vehicle, attaching drugs, right? So one of the holy grails of nanoscience is to use nanoparticles as drug delivery vehicles. Problem is that most of the nanoparticles that are used are highly toxic. And in fact, if you take most materials and you make them really small, like even gold becomes highly reactive in nanoparticle form, right? Maybe not such a good idea to be putting that into your body. Here we have a vehicle that naturally breaks down. Not only does it break down, it actually results in food for the body as a result of that. The most promising results that we're currently pursuing come from another modification of these particles that have been shown to have a dramatic effect on the immune response of organisms. So the native particles on their own don't have an immune response. But a certain modification of these particles can either upregulate or downregulate the immune response. And in particular, the downregulation of the immune response is really interesting because it can be used, for things like organ transplants and so on, but also in the production of vaccines. And preliminary data shows that we can increase the efficiency of vaccine production not by a factor of 2 or a factor of 3, but by a factor of 1,000. So it could, in fact, be a game changer in the production of vaccines. So maybe, you'd be able to get the flu vaccine of the week instead of guessing 6 months in advance and getting it wrong. Okay, so with that, I will finish. If you have any questions about some of those applications or some of the products, please feel free to ask me. I've told you about this wonderful nano from nature, these little balls that are safe and non-toxic, even edible. The reason why they're so interesting is that they have a special dendrimeric structure that leads to special properties, and in particular, a unique, strong interaction with water and also allows them to be used as a new model soft colloid system. So this is a promising new material, both for fundamental research and new technologies. So with that, I will just put up a slide. These are people who have done work in my lab at the university. These are people within Mirexus, many of whom have worked in my lab at the university, and then our collaborators at Oak Ridge that did the neutron work. Thanks.
Thank you very much for showing us how physics can be fun and entrepreneurial and making money and rejuvenate the skin. We have plenty of time for questions, so let's start with your friend over there. Steven.
Ordinary garden variety cornstarch, when you make it wet, has the property that it stores lots of water inside of each starch particle. And as it dries out, this causes it to crack in a consistent way. Which has geological applications. In particular, it cracks into little columns. And in fact, the only material we know of that does this is ordinary garden variety potato starch or cornstarch. What does your material do when you make a thick, a centimeter thick sample of it and just dry it on one side and it's mud?
Yeah, I think it would, you can form it into a film, but the film does not have very strong mechanical properties, and so I know. So what I'm saying is that it probably will crack, especially if you try to enhance that. The idea here is that these little particles don't really interpenetrate one another, and so the forces that are holding them together are not very strong. So I would expect that you would see probably some interesting morphologies. Well, next year. Yes. So with the starch granules, does the cracking occur between the granules then? Yeah. So similar, right? Particles that don't interpenetrate, yeah. Yep. Okay. Interesting. Huh? Okay.
So why the water is so ordered inside? Is it just because it's confinement inside the confinement of the order, or because the hydrogen bonds in the sugars are arranged in some hexagonal way?
I think it's probably a combination of two effects. One is the large number of OH groups that's available to replace the bonds that would have been there in the bulk water network, right? But also the individual chains of the glucose strands form into helical strands. And perhaps that helical channel geometry helps to enhance that, because the water ordering in this form of this glucose-based polysaccharide is, the water structure is more highly ordered in this particle than it is in other glucose-based polymers. So it has something to do with the structure. And possibly it's these helical channels that conspire together with the abundance of OH groups to give you a high degree of ordering. I don't know. We need to do more measurements with other techniques. Yeah, you can do that. Yep. Yeah, so if I have a dispersion of these particles, how do I get them out? So, yeah, so the way it's done on an industrial scale is to use something called spray drying, okay, where you take a slurry, rather concentrated slurry of these particles, and you pass it through a cyclone, basically. And the dried particles accumulate on the outside of this container. If you want to get, sort of more sophisticated, you can freeze dry them. Like you can use a lyophilizer to create dried particles from a slurry as well. But it's fairly straightforward to do. Yeah, so there's, I don't know if I would use the word stickiness. I guess there is a strong tendency for a lot of bioactive compounds to associate with these molecules. I don't know if I would call that a stickiness. It really does depend upon the chemical nature of the molecule or particle that you're talking about as to whether or not it strongly associates or not. You can enhance that by modifying the particles. So one thing you can do, for example, is add oily chains onto the outside of these otherwise hydrophilic balls and render the particles hydrophobic instead of hydrophilic. And then hydrophobic compounds like vitamins and drugs will have a stronger tendency to associate.
So I remember reading that if you put ordinary starch into corn starch into corn syrup, and then you have a strong electric field through it, and make the electric and form changes, they not solidify. So I wonder if you have like similar electrical increase.
Yeah, I'm not sure. The charge on these particles is almost zero, so I would, well, maybe strange things happen at large field strengths, but I wouldn't expect necessarily that electric fields would have a strong effect. I'm not sure. Maybe worth a try. So more and more we're beginning to think of these particles as having hairy bits on the outside. So they're probably sterically stabilized, I would say. So the hairy bits prevent the particles from coming close enough together so that van der Waals wins, right? So that's currently something that we're trying to sort out, both through measurements in which we use acid hydrolysis to degrade the particles from the outside inward. If there are hairy chains, then these are removed very quickly. We have some evidence for that. And then also Hendrix simulations of these particles indicate that there should be hairy bits on the outside. So the puzzling thing is then, why are they all the same size? If they've got hairy bits on the outside, why don't they just keep on going?
Why 30 nanometers? Why 30
Yeah.
nanometers?
Yes.
Why don't they go to 20 or 40? I mean, what determines the size?
So what you find, we did all of these measurements on different types of corn, and different types of corn create different size nanoparticles. Yeah.
We can have a label in the supermarket.
So within some range, right? So maybe the particle size can vary by as much as a factor of 2, depending on the source. And
because the size, 30 is like the size of a virus.
it's actually a very useful size from a biomedical point of view.
Exactly.
I mean, if you look at the literature for the uptake of gold nanoparticles by eukaryotic cells, it sort of has a maximum around 35 nanometers. So we know from experiments, so we've fluorescently labeled the particles and then introduced them into cell lines, and we see that they're readily uptaken into the cytoplasm of a variety of different cell lines. So that makes it very attractive from the point of view of drug delivery, if that is also seen in vivo. So.
Take one last question. Vegas?
So can it be that glycogen is a part of the kilon as well?
Part of the?
Kilon, the starch center?
Oh.
Because they are in the same place.
Yeah, I don't know if that's known, first of all, but I'd be a little bit surprised if that was true. I mean, the differences between starch and glycogen have to do with the density of branching. So in glycogen, These linear chains are not very long before they branch. They're maybe 10 to 13 glucose units between branch points. Some starch, maybe, yeah. Yeah, maybe some starch.
Thank you
Okay.
again